Greetings to all of you. Welcome to CodeStream. This is second video of my DBMS series. I hope you have watched the video on transaction, which is very important DBMS topic. This is a following up video on the transactions topic because concurrency control is very important in transaction. So let's dive into the topic. Now, what we'll cover in today's video, I will cover schedules, that why we need concurrency control, anomalies, serializability, log-based protocols, deadlocks, timestamp-based protocols, and at last we'll make a comparison. Now, what is a schedule? So, it is a chronological order in which operations like read, write, commit of multiple transactions are interlinked for execution by DBMS. So, I just read the PowerPoint presentation. What it means that the schedule is an order in which actually you can say that schedule is a group of multiple transactions. I told you about the transaction in the previous DBMS video, which is a ordered sequence of the operations such as read, write, and commit, and the group of those transactions, which is ordered sequence of operations, is schedule. So when you see there are multiple transactions, you can say this is a schedule. But yes, order matters. I also have written, if you see the red order matters because it determines whether the final database state is correct. Yes, so order matters. So I will cover you with the serial and non-serial schedule. Serial schedule. First transaction commit itself. First transaction commit itself. Then the second transaction starts. It's a serial schedule. And the first transaction has not committed itself yet, but the second transaction starts. This is a non-serial or concurrent schedule. So you can see that here we have a schedule which says read A, write A, commit. Then when this completes, commit means we have a final entry to the database permanently. So commit means we are permanently and permanently saving the state of the transaction into the database. Now we are moving with another transaction which starts, but it starts after the commit of the first transaction. But in non-serial, it doesn't happen. I explained it to you earlier in the previous slide. So why concurrency control? Lost update, dirty get pattern. So a committed update overwritten by another transaction. When a updated committed, and then another transaction comes and write it again. So here I can give you the example that suppose we have two transactions, transaction 1 and transaction 2. I write something on the data B and commit that this is saved. But I write another thing after commit in the transaction 2. So the data of B is changed, but it is committed before in the database. This is called lost update. Update is being happened, but it is lost because the database is already data of B is already saved permanently in the database. Now we'll come to the dirty read. Dirty read. Transaction reads data written by uncommitted transaction. You know what I'm talking about. Let me erase this. Now, for example, I write something on the same data B. Now it is not committed, but I read data from the transaction. So you all will say, what is the problem here? The problem is when transaction one commits itself after the not commit, sorry. I'm sorry, not commit. I want to say not, uh, just a moment, please. The problem is when the transaction one failed and it rollbacks. Nothing happened. Let me write the rollback. Rollback is RB. Rollback to the initial state. What happens is transaction 2 reads the wrong data which is uncommitted. For example, my account has 10 rupees and my account received 10 rupees more, but that transaction is failed. So, so according to the rules of transaction, asset properties, atomicity should be there. If transaction is failed, it should not happen. So the money get back to the sender's account and my account is already 10. But in between this process, when the money credited into my account, credited into my account, then in between somebody came and read that my account has 20 rupees balance. So that transaction says no, Tushar's account has 20 rupees balance. But after that it failed. So that transaction reads the wrong data. It rollbacks. It is called the dirty read. When you read the data which is written by the uncommitted transaction. When the transaction is uncommitted, you should not read any data because it can fail, or you should be ending up the reading the wrong data. Phantom read. A transaction reruns a query, finds new rows that satisfy it. Yes, same thing, which is done with the dirty read. Here I write into one data column. One data, you can say one atomic cell. But when it comes to the rows in a table, when I write row in a transaction and it is read by someone, some other transaction, and but it is uncommitted and failed, it is called phantom read. It has the same analogy as dirty read, but it takes the rows of the table as the data. Now lost update problem. So here is the occurs when two transaction read the same date item. Okay. Then both write back updated values. One overwrites permanent and permanently loses the other's update. Okay. It is in simple language. Let me erase this so that you can read the definition. For example, lost update problem is that I have a paper. I'm giving you a very layman's example. I have a paper. I wrote here 20. This paper suggests my account number. Not account number, sorry. My amount in the account. My balance. Balance. BAL. So this is it. One transaction came and updated to 30. I said okay. And another transaction at the same time read it and again updated to 20. This is called lost update problem. I didn't see read the last update, which was 30. I didn't know that 30 happened. My account balance was increased. This is lost update problem in layman's language. Now you can read the definition. It says occurs when two transactions read the same data item, then both write back updated values. One overwrites and permanently loses the other's update. That's what happened with my account balance. Now let me walk you through the example. These are two transactions which is showing balance in account. Now transaction one read A means it reads the balance. Okay. Balance is 500. Okay, it reads it. Okay. Now transaction 2 reads it. Okay, it is 5. Okay. Everything is fine up to now. Now there is an update. Transaction 1 adds 100 rupees to my account. Okay. It's 600 now and write it. That means it is updating it on the log, temporary log. Now the same thing done by transaction 2. It updated to okay 700 it becomes. Okay. Now you might be thinking that if account balance is 600 in the upper row, why you are writing 500 plus 200, not 600 plus 200? This is because when the T2 reads that A, it was 500 and T2 knows that I have the A which is 500. So here 500 is transferred and this happens because 600 done by T1 and T2 is not aware of that. So both the transaction read the same data, but one transaction write it first and then another transaction rewrite it. Final is 700, can be 600 also. This creates an anomaly. This is an anomaly that what do you want to do? You want to add 200 or 100? This should not happen. This is a lost update problem. We have an update that shows that your account balance increased with only 100 rupees, but now it is showing it is increased by 200 rupees. So we lost an update which says your account balance increased by 100 rupees. So we have added the value like 100 from transaction 1 and 200 from transaction 2. Total value added to my account is 300. Okay, but the final value is 700 because it is separated separately readed by the transaction. So this creates an anomaly. I have lost 100 rupees. Why? Because I have 500. 300 should be added in my account to get my balance, expected balance 800. But my expected balance shows 700, which makes me loss of 100 rupee. This is the lost update problem. That you added two times and you get the value of adding only one time. You lost the previous update that should be updated, but it is not updated because of the asset property which says integrity that no one disturbs each other's transaction. Let's move to the other anomaly. Dirty read problem occurs when transaction reads data written by another transaction. That's what I told you. That is not yet committed. If the writer later rollbacks, the reader has value never truly exists. I have explained you before about this. Now you will see the example. Now we have 500 in my account. That is very universal. I have only 500 rupees. Now it is updated to 600 but uncommitted. I have not updated in my real database, which is a bank database. Bank didn't updated its database, but saved it in temporary log or cache. So my account becomes 600. Now another person comes and read, okay, Tushar has 600 rupees. Uh, I have lent him 500. 500, he should definitely give it. Now what happens? This rollbacks. Error happens, which can happen in any. Now T2 says, okay, Tushar, you have 600, you can give me 500. Now I don't have 600 actually. I have 500. I reverted back. So how can I give T2 500? So that means T2 reads the wrong value. Okay. T2 reads the wrong value because the value inverted to 500. T2 reads the wrong value. I cannot give him his or her 500 back because I don't have it. Only have 500. I cannot give my full money. That's an example, layman. But you see that T2 now reads the value which is not exist in the real world. So this is a very bad anomaly. For example, you see that a transaction happens on your side. Somebody sends you money and says that I have deducted the account, but my account is updated, but mine is not. But their account is updated that the, the money is deducted from their account, but not from the my account, but not added to the my account. So this also create this type of problem. So when you read the invalid value, that creates a dirty read problem. Unrepeatable read and phantom read. Now we are covering phantom read, which I have told you about the rows. Unrepeatable read and phantom read. Okay. A transaction reads the same data twice, gets two different values because another transaction modified it. I read it 500, updated and committed it. Now it becomes 800. Okay, fine. This is also an anomaly because this is also an anomaly because you can't have one transaction can't have two data when this transaction didn't updated the A, why it is showing 800. So this is also an anomaly. Same happened with phantom read. I told you in the previous slide that it deals with the rows. Now it reads the 5 rows. Now one row also inserted. Now it reads the 6 rows. You might be thinking it is very general and okay. When data is updated, you should see the new data. That's fine. But in transaction, one transaction should not disturb the other transaction, which is a rule. That's why it creates an anomaly. It follows it violates the property. So let me go through the serializability. So how to solve this? To solve all these things, to solve all these things, we have to make our transactions serializable. For example, you have random things happening around you. You have Let me give you an example. You have a shop. You have an open public shop. No one is there. Public shop. Yes. A man came and picks something and go because it's a public shop. So you don't have to pay. It's all free. You can just pick and go. Okay, that's fine. Now another man come, not in the same line, but from the another line. Okay, and picks the same from the same shelf. Another man comes, also want to pick from the same shelf. Another man comes, which want to pick from the another shelf, but that shell is also occupied by the another. So this creates a ruckus. This is non-concurrent. If we try to make a line where all the people are standing in one line, serial wise, and take their item one by one, it will be very useful, efficient. No anomaly should be there. That is what we are going to do in serializability. So when we cover serializability, we should read this. Schedule is a serializable if its outcome is equivalent to the some serial execution of same transaction. It is correctness criterion of the DBMS aims to guarantee every concurrent schedule. It allows performance benefits of interleaving without sacrificing correctness. Okay, there are two types of serializability. One is conflict serializability. A schedule can transform into serial schedule by repeatedly swapping the non-conflicting adjacent operations. We can swap the operations which are in conflict and it, test it by making the graph. See, we'll see in upcoming slide that how we make the graph in which is called precedence graph. We will make the precedence graph and see how conflict serializability. I sometimes fumble in these pronunciations. Serializability, conflict serializability. So what it does, it makes you the graph, precedence graph, and when the graph is cyclic, you have conflict. And graph is not cyclic, your schedule is serialized. So we also have the view serializability, which has some conditions to follow. These are some conditions. Initial reads, final writes, and each read source match. So what it says, initial read, first condition, initial reads should be common between two transactions or three transactions. Final writes should be common, FW. And the third, but very important, the order of the the order of operation should be also same. Order of operation also same. So these things should, if these are same, then it is view serializable. But there is no testing like making graph or actually what happens that we have, I will cover you with that graph and that analogical. Let's move to the next. So let's come to this topic, conflict serializability. So here we make precedence graph by marking arrows between the nodes of the transaction. Now, how these arrow marks? These arrow marks between some conflicts. Here C represent conflicts. Conflicts are read write, read and write operations. are in this order. Write read. This is also a conflict. And write. These three conflicts should be looked and check whether there is a possibility to mark arrow between two nodes. So uh, conflict serializability checking is there. Okay. Now we will make the graph by checking these conflicts. Read write, write read, write write. So we have the read write conflict here. So we can make arrow from T1 to T2. Now we have write read conflict here. We can also make an arrow from T2 to T3. We have again read write conflict here. We can also make an arrow. Okay. Now, can you see that there is no cycle in this graph? No cycle when the cycle is the format or description where when you start from one node, you reaches that node again. So there is no possibility to reach the same node again in this graph. So there is no cycle. If there is no cycle, then it is conflict serializable. CS for sure. And when any schedule is conflict serializable, you can say it is also view serializable. We can check view serializable separately, but when it is conflict serializable, it is surely view serializable. But when it is not conflict serializable, we should check for view serializability. Okay, so I am writing here. If it is conflict serializable, we can check it is already view serializable. If it is not conflict serializable, you should note this because it is important. We are going to have some problems, statements, and we will solve that. We can check the view serializable. It may or may not be view serializable. We can check that if it is not conflict serializable. So let's move to the next thing. So here we view serializability is this is a surface level serializability where we check these three conditions. Initial reads should match. We should read the same data value as we read in one transaction as we read in another transaction. We should update in the same order. We should finally write the same data among the transaction in a schedule. So these three conditions should be matched. Now you all must thinking that "Hmm, I don't understand this condition. This is very confusing." So I will cover you with this cover you with the example to see this. Now let me walk you through the examples by solving some problems. Okay, here also written a schedule is view serializable if it is view equivalent to some serial schedule. If conflict serializable schedule is also view, the reverse is not always true. As I said, conflict serializable is always view serializable, but reverse is not true. View serializable is not conflict serializable. If the schedule is not conflict serializable, we can check whether it is view serializable or not. Let let's move to the let's move with the problem. Here we have to solve this problem which says check whether the given schedule S is view serializable or not. So I told you if the schedule is conflict serializable, then it is already view serializable. If it is not, well, then we have to check. So what are the conflicts? Conflicts are RW, WR, and WW. Everywhere, every pair is a conflict when right operation is there. You can see right is common. So right is enemy of everyone. Because right is enemy because of we have seen anomalies that we have write the thing that it is not there, it does not exist. We read the thing that we write it before and roll back. So that's why right is making a conflict. So we have seen the conflicts in the video, that is lost update conflict, phantom read conflict, dirty read. We have covered this. You can revisit that slide if you want to, if you want me to re again cover that. Now we'll look for these conflict. So we have these conflict in here. So T1 writes A. Any other transaction has to do with A. Can you point out? I don't think anyone has to do with A. Okay, no. So for A data set, there is no conflict. Let me cover him. So T1 write B. Okay, now we have something interesting. We have WW conflict here. As T2 write B, T3 also write B, and T2 also write B. So there will be three arrows towards T2, then towards T3, then towards, because after T1, three transactions write the value of T. So there should be three values, three conflicts, three WWs for T1 and T4. Okay. Now for T2, there are two transactions which makes the WW conflicts. So T2 go to the T3. So let me make this graph neatly so that you can understand, because this becomes so messy. So for T1, we have T2 on there, and we have T3, we have T4. So these three are sharing WW conflict. Now with the T2, there is conflict between T2 and T2. After T2, we have T3 and T4, which writes on B, and before T2 writes on B. So this is a WW conflict again, two WW conflicts for T2. So T2 has conflict with T3. Also, it has conflict with T4. So now coming to T3, it has only one conflict, which is with T4. Okay. So let me check the cycle, if there is a cycle or not. So here we go, here we go, here we go. No, there is no cycle, because this graph you can see from my laser that this is breaking the cycle. T1 to T4, breaking the cycle. And here is we from T4 to T2, where we are not having a cycle. Let me check this internal. T1 to T2, then T2 to T4. We have not cycle here also. We do not have cycle here also. So this graph is acyclic. Acyclic means no cycle. This graph has no cycle. So if the graph has no cycle, then schedule is conflict serializable. And if the schedule is conflict serializable, I told you that it is automatically view serializable. We don't have to check it. We only check when it is not conflict serializable. Okay, so graph is acyclic. I cannot see any cycle because in this yeah, no cycle. T1 to T2, then T2 to T4, no cycle after that. T2 to T3, T3 to T4, no cycle after that. So there is no cycle. Let's do this example. Now you know the conflicts CS, R, W. When W is here, conflict is here. W is such a bad luck. In real life, W is win, which is good luck, but in DBMS, it is bad luck, specifically in transactions and schedules. So when we go to T1, when we go from T1, let me check the conflicts here. This is conflict. This is conflict. Do I have more conflicts here? Yeah, this is also conflict. So let me cover these conflicts one by one. We should now. So this is conflict from T2 to T3. T2, T3. This is RW conflict. Okay, I make that this. This is also conflict. WW conflict. T3 to T1. Okay. Do we have one more conflict? Yeah, we have one more conflict, which is T2 to T1 because T2 writes A first and then T1 writes, sorry, the T2 reads A first, then T1 writes. So T2 to T1, there's a conflict. T2 to T1. Okay. And do we have more conflict? Let me check more conflicts here. We have conflicts between T2, T3. I have marked it. We have conflicts between T1, T2, T2 to T1. Do we have conflicts between T1 and T3? Yeah, we have. So if you can see, I erase it all to mark you the conflict. We also have conflict. Read is first done by the T1 and then it is done by the write done by the T2. So where we have RW conflicts many times. Approximately we have three RW conflicts and one WW conflicts. So T1 to T3 arrow should be there. You should understand this. We should find the conflict between every transaction. We should make pair between all the transactions and check whether there is a conflict or not. So I am checking T1 to T3. T1 to T3. Okay. Okay. Unfortunately, we have cycle here. Cycle. So this is not conflict serializable. Conflict serializable? No. No conflict serializable. Okay. So we have to check the view serializability. Initial read should be on A. So these two transactions have the initial read on A. But the third transaction is not having an initial read on A. Okay. Final write on A. So these two have final write, but this is not having. So I don't think it is view serializable also. But you should check view serializable. It can be view serializable as well. So here it is. We have done with the conflict serializability and view serializability. We will cover more topics on this topic. This is a part one video of conflict serializability. Actually, concurrency and serializability. This is a part one video. In next part, we'll cover the more we will cover more topics and we will get more deep down to. Thank you so much. If you're watching up to this mark, please hit the like button, subscribe my channel, and show support. Thank you.